back, and what is here? Welcome to this video. So in this video, I'll be trying to explain to you one of the few questions that came into my mind when I'm saying like computer, RAM, I don't know, anything that you might just stumbled upon. And I think it's time for some questions, and it's time for some answers too. I had a lot of time just researching this stuff on my own, and okay, classes in college weren't enough for me just to explain, for example, operating system or architectures on any kind of information. So I had to go on my own and research this stuff on my own too. Yeah. So yes. Okay. So I think there's one thing that surprised me, like, when I was like researching on my own, was that I think it's a kind of surprise, but the computer itself was actually really interesting since I was like okay doing a lot of stuff on my computer since I was like I don't know 12 or 13 years old, but I didn't know like such a thing exists. So the one thing that surprised me over and over again, I think, is while trying to create this video is how simple computers are. Like it's still hard for me not to teach myself out like expecting much more complexity out of this box that is in front of me, but okay, I think a lot of abstractions are actually existing. But if there is one thing like you should burn into your mind while trying to travel this journey with me is that like everything that seems simple is actually that simple. Um, and that this simplicity is very beautiful and like sometimes it's very cursed. Yeah. So just let's start with the basics of how your computer works at its very core, like the very basics. Like um like the central processing unit, like the processor. Yeah, we will be starting with processor and we will be trying to explore other stuff like any computer, but let's for now just focus on how computers are architected. So the central processing unit, which is the processor in your computer. So this is the little piece, and you can just look at the picture. Why not just a picture? Yeah. Okay. So this is a CPU. So the central processing unit, which is in your computer, like it is the one that is in charge of all the computation, and it's like the big cheese in your computer. And it starts, I think, chugging as soon as you start your computer. It starts like working automatically when you power on your computer. And it's the one that is responsible for executing instructions after instruction after instruction, all the instructions that your computer is doing. So, for example, you are now watching a YouTube video, yes. So, this YouTube video, the one who is responsible for executing the instructions of the browser that you are watching the YouTube from, is the processor, which is pretty obvious thing. So, I think just a little history. Just I remember the first processor was the 4004, I think. Yeah, it's the 4004. This is the kind of the first processor that was invented. Like you see this little piece, it was invented in the 60, I think. In the 60, I don't know. I don't remember exactly the date, but I remember it's I think it's in the 60. Yeah, I don't remember actually the engineer who engineered this thing, but it's actually a fascinating one. So I think it's a six. Is it a 6-bit or a 4-bit? I don't remember. I think is it a 4-bit? I have an issue just remembering the kind of stuff. Okay. Yeah, it's a 4-bit. Okay. So it's a 4-bit um, CPU, and what do we mean by 4-bit? It means that the instructions are of the size of 4-bit. 4-bit instructions, yeah. I think like compared to what we have now as computers, like the computers now are 64-bit systems, but I think 64 bits are quite huge compared to 4-bit now. I mean, since the 60s. But okay, I think it's was far less complex than modern processors now compared to what we have now in a computer. But I think a lot of complexity or a lot of simplicity, I'm sorry, I think still remains. Yeah. So Now the question is, the instructions that the CPU executes are just binary data, I think. I suppose everyone should be knowing. Okay, what does a binary data mean? So for example, let's suppose you are now just, so this is a CPU and this is, I will be giving him a binary data um, that he will be trying to execute. So for example, let's say he is going to execute this one for me. So, and he is going to give me an output. The output should be something like the instructions. For example, let's say I want to do, for example, on the code, I have coded int x equals to 1. This int x equals to 1 should be converted into something called machine code that the processor will be executing in order to get the int x executed. The int x equals to 1 executed. So this is exactly what the kind of instructions that the processor is executing. And everything you can see in the computer is a set of instructions. It doesn't matter what the kind of programming language you are using, as long as the result is going to be a machine code that this specific processor is going to execute. So um, so basically, processor are just executing this binary data. It can be a byte or a two. What does a byte mean? A byte means actually just a 4-bit value, an 8-bit value. I'm sorry. For example, I don't know. This this for example is a byte. This is for example a byte of data. I don't know. We can also have 2 bytes, which are just a copy of that. Just copy it for example. This is 2 bytes of data. It can be 1 byte, 2 bytes, I don't know, 3 bytes. It depends on the processor itself, how it's going to get the instructions. But the instructions are in the formats of bytes. Um, and if you can just give it a lot of abstractions, let's call it bits. But yes, just representing one instruction is being run, which is called the opcode. We'll be trying to see that. Um, we just we'll be just trying to explore more what an opcode is doing. Um, but there is one thing that I have to say is that we are going to see a little bit assembly, a little of assembly now, but I will be having like a dedicated video for assembly just to explain what assembly is doing and a crash course of assembly, the different kind of instructions that we can have in assembly. It's a kind of low level, not class, but just a video. Yeah. Um, follow it close. So what do we have also? Um, so we will be having a kind of opcode. So for example, let's say you wanna add something and you want the processor to add, for example, 2 plus 3. So basically you got to put the 2 into something and the 3 into something. Okay, we'll be seeing that after just explaining more what the machine code is doing. We'll be back to this. Just forget that. Okay. So basically now we have machine code in front of us. Let's just write that into the black note. So we have machine code, which is for example, let's just say for just an example, 111 0111, and let's say for example 0001 0010. Let's say for example last one, which is 000111. For example, this is linked. Yeah. So this is machine code. This is what actually the processor will be executing. And now, if we just try to convert that into the hexadecimal machine code, let's say, and now it's in the hex, I don't know, we might get something like 0xf7, I don't know, 0x1 and 2, and 0x 0f. So for example, this kind of machine code in the hexadecimal means something. For example, it's just an example. It does not mean that it's necessary the truth or it's necessary correct, but it can be, for example, turning into this assembly. Assembly is a kind of low level language just for us humans. for us as humans we can understand. So for example, let's say it's add means that it's going to be doing an addition operation. For example, ABX will be going back to this one. ABX, let's say 10 for example, or 0xf, which is in this value. So that means, for example, if the 0xf7 is called an app code, it means that it's going to be mapped to the app. So when the processor is seeing 0xf7, he is going to go into the circuit that he has out there and just find the mapping of the 0xf7, and he will be just, for example, trying to just figure out that the 0xf7 is the add, and the 0x12 is actually the calling to this, to, let's say, variable called dbx. So and the 0xf is going actually to add this value to the abx. So for example, this instruction is going to do abx equals to abx plus 0xf. So this is what actually will be happening. So this is the destination of the result, and this is the source, and we will be exploring that in one video called the assembly crash course. Don't worry, just for now you are trying to understand how your processor is doing that. So this is at the low level of what the processor is going to execute. This is the machine code and the hex. This is the assembly that we can get, and there's an interesting assembler and disassembler. So assembler is something when you assemble some code, and disassembler is when you give him, for example, this instruction, and he's going to give you the machine code in hex. So this is interesting just to play around with this stuff. So for example, let's say we have add EIX. EIX is another variable um, that the processor is using. So let's say for example he has 0x, for example, I don't know, 1. Let's try to assemble that in the architecture 86, and because there is a difference between the 86 and the 64, and we'll be exploring them also in the assembly video. Yeah. So, for example, when we assemble the add EIX 0x1, for example, when we try to add 0x1 to the EIX, we get something like that, which is 83C001, which is like, this is what the machine code in hex looks like when the processor is going to execute. So basically, the processor is going to execute this stuff. Now, let's try, for example, to disassemble this and try to get the instruction that we had. Okay, so when we try to disassemble this, we get add EIX 0x1. Let's try, for example, to play around that. Let's change this 1 and try to, for example, change it with, I don't know, for example, 3, or let's say 4. When we try to assemble that, it's actually going to give us 0x4. So when you change the machine code, you change the behavior of the assembly, and when you change the behavior of the assembly, you can change also the machine code, which is really interesting. Now, for example, when we let's try to change this, for example, to 1 and see what could happen. It becomes ECX, another variable, which is really interesting too. Let's say, for example, I want to change the 83 to 84, for example. Let's see if it's going to change the add into something else. It becomes another assembly code, completely another assembly code. It becomes a test, which is trying to test if the CL and the AL, two variables actually, and it's going also to give you another assembly code, just point wide 0x4. Okay, that means that when you change the machine code of the instructions that you have, you're actually changing the behavior of the code or the assembly code itself. So that means now that all the programs that you have in your computers, from Google Chrome to whatever you are doing with your computer, is actually like that, and your processor is executing this actually. So this is what happens exactly. Now, just an aside, let's go back to the add, for example, ABX, for example, 10, just to explain a little stuff. Okay, something went wrong. Okay, assemble. Okay, so this is the add EBX 10. So we have add EBX, which is 0xa, which is a 10. So just aside, instructions aren't always just represented like 101 in machine code. Now, for example, that does not mean that the add will be always converted to to 83, and the EBX will be always converted to C3, and the 10 will be always converted to 0A. It's not like that. And the proof to that is that if you remember the example that we did earlier when we changed something in the bytes that we had, the instructions became from one assembly instructions to two instructions, which is the test and the 0 byte. I don't remember the other. Was it 0x4? Yeah, 0x4. Yeah. So instructions aren't always represented one-on-one in machine code, as in the code that we had. So, for example, this add, let's say just for example, add EIX. I don't know, 512, for example. Yeah, let's try to assemble this. Okay, as you can see, it became much more larger than the one that we had. It's not a one-on-one machine code. Yeah. So, for example, in this instruction, the first bytes are the 05, are the opcode, specifically just representing to uh, and adding for this specific variable, which is the AIX, to just a 32 number, which is the 0x200. And another interesting thing is that, as you can see, the 0x um, 200, I'm sorry, is in something called Little Endian. So what are Little Endians exactly? Just to explain this briefly. Um, so Little Endian is a kind of concept that the processor are doing when trying to read or write values into, I don't know, instructions, data, whatever it is. For example, when you have this value, which is 0x200, as you can see, the 0x200 is like 0002. Forget about this zero, just focus on this. They are like in the reversed way. So, for example, when he tried to write them like in memory, he's doing like 002, 02. I'm sorry. So this is the 200. And just to understand more what this is doing exactly, let's try, for example, to take this and disassemble it. When we try to disassemble that, um, we get, for example, this. Let's try to add, for example, at the end two, just to see something. Let's say 3. You see, we got 200 and then another huge number. So that means that this number is read in the reversed way. 3 0 0 0 3 0 0 0 2 0 0 2 0 0. You see, that's in the reversed way. That's called actually Little Endian. So Little Endian basically is when you take any kind of value like that or address or whatever, and when you try to do it in the Little Endian, you actually you actually had to write it in the reversed way. But it's when it's in the Big Endian, which is the other one, you actually just have to write it as if it was the same. Now I suppose you kinda know when it's in the Little Endian and when it's in the Big Endian. So for example, when your software or when your program is using the Little Endian convention, you should be able to just think about when you, for example, when let's just say you want to modify the machine code in a way that you want to change some values into it. So when you try to just this actually when you try to modify the machine code of a program is called patching. For example, when you try to patch, I don't know, a program to behave in another way, let's say you want to change the value 3 to value 2, you got to think about the Little Endian and the Big Endian, and you should be able to know the type of the program or the binary that is using the Little Endian or Big Endian just by trying to use a file on that program and see if it's in the Little Endian or in the Big Endian. Yeah. So this is all about the machine code and the Little Endian, the Big Endian, and everything. Now maybe it's time just to go back into your RAM and just explore a little about what your RAM can do now. So what do we have now? So your RAM is like your computer's main memory bank. So it's a large multi-purpose space like which stores like all the data used by programs running on a computer. That includes like the program code itself, I don't know, as well as the code at the core of the operating system too. Like the CPU always like reads machine code directly from RAM, and code cannot be run if it isn't like, I don't know, loaded into RAM. So the processor is basically using the informations or the data from your RAM. So actually he do two operations to get that. So he either write into the RAM or he either read from the RAM. So he reads the instructions, he can read instructions, he can read data, he can do like whatever he needs. He actually needs to check the RAM to make sure that this data or this instructions is loaded from the RAM. So we'll be trying to see that when we dive more into the execution of a program. So for now, just make sure that you understand what the RAM is doing. So the RAM is just a place or a space where programs are just running on a computer. So it's a space where you can put the program just to run. And the program could be anything actually. So it can be, I don't know, it can be an operating system, it can be a program, it can be whatever. So it contains this machine code. So the CPU like stores an instruction pointer actually, which is an interesting variable too that the processor is using. And the instruction pointer points to the location in RAM where it's going to fetch the next instruction. Um, so actually, let's suppose there is a program in here. Program. Actually, let's say the instruction pointer is here. A pointer is actually just, let's imagine it's like an arrow key like that. And this is the instruction pointer. So the instruction pointer will be pointing to this place into the RAM. So the instruction pointer is something that can help the processor or the CPU to know where is the instruction to be executed or where is the next instruction to be executed. So this is basically the main job of the instruction pointer. So it will be just pointing to the location in RAM where it's going to fetch the next instruction. So after just executing each instruction, the CPU moves the pointer and repeats the same thing. So we call this actually the fetch execute cycle. So for example, when we have the fetch execute cycle, we have something like that. It's just a cycle where you just repeat stuff every, for example, slice of time. Execute. Yeah, sorry for the bad writing again, since I'm writing using my mouse. So fetch and execute are two kind of let's say operations the processor is doing each time, like infinitely, whenever you are trying to well, just once you turn on your computer, your processor goes into this cycle, which is fetch execute. So he reads instructions for at the fetch operation, for example, he reads instructions like from memory, which is RAM, at the current instruction pointer, and the execute is just like saying to the CPU, hey, could you please run the instruction and move the instruction pointer. So for example, once you fetch an instruction, once you fetch it, the processor is like saying, okay, I will be reading from this place this instruction, and then I will be just putting it in a place, just trying to load it. And then once you load it, it's time for execution. Okay, once he's trying to execute, there is another steps actually in the execution. It's not like executing directly. There is a phase of like there is a phase of like just decoding the instruction, because it's like, as we can see in here, for example, it's 050002. He needs to make sense of all of that. So that's the part where he needs to decode the instruction before executing it. Yeah, so this is just the fetch and the execute um, cycle. So after just executing an instruction, I think the pointer just moves forward to immediately after the instruction in RAM. So for example, once he executes an instruction, the IP should be going from this place to another place, which is the next instruction, for example, and so on. Um, So once he just moves forward to immediately just going into another instruction, now it points to the next instruction, which is, for example, this one. Um, and that's why code runs. So the instruction pointer just keeps going on and on and on and on, just executing the machine code in the order in which it has been stored in memory. So, like some instructions can tell the instruction pointer, for example, to jump somewhere else instead, or jump different places depending on a certain condition. Like just a little example of this is to understand what I'm talking about. Let's imagine you have an instruction like this one, 0x1, 0x2. This is like just the number of the instructions. This is another one, which is another instruction. Let's say, for example, the first instruction that you had is x equals to 1. The second instruction is x equals to 2. The third instruction is equals to x plus y. How the hell the processor is going to execute this? Well, the first thing that he needs to check out is the instruction pointer, which is the IP. So the IP at first, this is bad, just because it's black. Yeah, white is better. This is the instruction pointer. It will be going from this um, this instruction. So the instruction pointer will be pointing to x equals to 1. So what does the processor is going to do? So what does the CPU will be doing basically? It will be getting this x, and he will be trying to make a variable for this x. Let's call, for example, this variable EIX, since the variables that the CPU will be using are called EIX, EBX, ECX, etc., etc., etc. Let's say he will be trying to put that into the processor. So just to make this better, okay. So what does the CPU will be doing? So let's say he will be just trying to move that that one into the AIX, and then in the second instructions, once he executes that, so I'm trying just to convert this x equals to 1 into an assembly instruction that the processor will be trying to understand eventually. So once he finishes that, what will be actually happening is that, for example, the IP here is equals to 0x1. Once he finishes executing this, the IP will be going to 0x2, and he will be pointing to that, which is the second instruction. Now the processor is needs to, for example, to convert this instruction into something else. And actually, it's not the processor who is going to convert the instruction for you. There is something called a compiler, and it is a whole subject that we will be talking about that is responsible just for converting this high-level code for you into machine code. So for example, when you do, let's say, for example, now you will be using another variable, which is the EBX, for example. Let's say 0x2. Let's get this one like that, which is better. Now, okay, once the processor executes this instruction, it needs to get the instruction pointer into another place, which is the next instruction. Now, the IP will be pointing to the instruction 0x3, and the IP will be going down. Okay, now it's pointing to another instruction which have the addition operation. Now it's time to add both of them into another variable, which is the z. Okay, the processor here has it's not like like actually the processor, but the compiler has the choice to either create a new variable which the CPU will be using, such as AIX or ABX, or just use the one that was in front of me or that's in front of you, like AIX, for example. Like we can use just AIX like that. Once we do that, like we have x plus y, which is the like adding the EBX to the AIX. What does this will do actually is we'll be doing AIX equals to AIX plus ABX, and the result will be an AIX. So actually, if this is a 1 and this is a 2, it's going to contain a 3. And then he can do his job and just return the AIX actually. So this is basically how the processor is doing a lot of instruction, and this is how he is mainly executing instructions in a computer. Now, what is more interesting is, let's say let's say we are now in the instruction 0x1, so the instruction pointer now is pointing to the instruction 0x1, and let's suppose we have an instruction in the 0x, I don't know, a 10, for example. I want the instruction pointer to go from 0x1 just to the 10 directly without just needing to execute the ones between the 0x1 and the 0x10. Thus, to do that, for example, we can just execute an instruction called jump. So jump can actually make you or make the instruction pointer jump from the instruction that it has in its own hand and goes to an instruction that you just have to specify. So for example 0x10. That will make actually the IP just goes to the 0x10. So this is basically called a special command in assembly, or a special instruction actually that uses, let's say, also a special variable called the instruction pointer. Yeah, so actually this will make the code reusable. So when I want, for example, to, let's say I have a block of code from 0x1 to 0x2, this code is doing something. I don't know, for example, summing something. It's doing a sum. Let's say in my program, I want to sum a lot of stuff. For example, I want to, for example, add 2 plus 3, and then I will be adding 5 plus 6. So to do this, you don't have each time to write the code of the sum again and again. Whenever you want to do an addition, all what you need to have is jump just to this block of code or this machine code block just to do the sum, and all you need to have is just pass the parameters, which are the 2 and the 3, the 5 and the 6, and so on. Yeah, so just going back again, so the instruction pointer is stored in something called register, which I have been called variable for you, just because you don't know what a register is. Let's just now give it its own name, which is a register. So registers such as AIX or ABX or I don't know, ECX or whatever I've been just calling them are small storage buckets that are extremely fast for the CPU to read and write. What does that mean? Let's create a new port. Just to explain this, so this is the CPU and it has a set of registers. The set of registers he is using. Sorry again for the bad design. Okay, so this is the CPU, this is the RAM. Now, what's interesting is that the processor, whenever he wants to do the addition, for example, of 2 plus 3, as we have mentioned in this place, as you can see, he is using um, the registers to do that. He's not like using the addresses or he's using the places in RAM just to do that. So, for example, the 2 and 3, okay, they are stored in the RAM, but he needs to fetch the 3, he needs to fetch the 2, or load it, or load them, I'm sorry, and then he needs to use the registers, I'm sorry, the registers to do the addition. So basically, what is happening when he is using a register is a lot. It's actually extremely fast compared to just reading and writing from RAM. So reading and writing from registers, it's a lot fast than just using the RAM. So this is the difference between just using registers and using RAM, like in terms of read and write. So like each CPU has its own architecture, so that's something we need to be like just fixing around, that each CPU has its own architecture, and by architecture we mean that it has its own, for example, let's say register. So for example, Intel processor has its own set of registers, ARM processors has its own set of registers, etc., etc. So it depends. So the size of the registers and the naming of the registers and all of that depends on the architecture itself of the processor and how it is designed exactly. So so since each CPU architecture has fixed set of registers used for everything from storing just temporary values, as you can see in this example, during, I don't know, computations to just configuring the processor. I will be trying to see that later on, just the configurations of the processor. Like some registers are directly accessible from machine code, like for example the EBX is accessible from machine code since we have seen that. Just like for example move add EBX 0x1 just to see that okay the EBX is accessible just by using the C3, just to make sure that the registers can be directly accessible from machine code. Like other registers are only used internally by the CPU but can often like be updated or just read using specialized instructions. One example is the instruction pointer, which cannot be read directly, but can be updated with, for example, I don't know, a jump instruction. What does that mean? For example, we have just I think I give an example of that. Just imagine the example of the 0x1 and the 0x10. Once I wanted to go from 0x1 to the 0x10, I couldn't just do like a move like IP 0x10. We need to, actually this will, in the logic of the move, it will be going to move 10 to the instruction pointer. But to do that, actually you have to use the jump. All you need to do is going just to do a jump to the 0x10 and that will eventually put 10 into the instruction pointer. So the instruction pointer is a kind of special register that is used internally by the processor, and it's very important because it's the one that is pointing to the instruction that will be executed. So since the processor is so naive, as we can see, maybe it's time just to go back to the original question that we have asked. So what happens when you run an executable program on a computer? And this is a question that we have to ask. But you gotta ask. It's it's very important to ask this question in order to understand the answer. So I think first a bunch of magic like literally happens to get ready to run it. For example, this magic I will be trying to explain a little of it, like 2% or 3% of the magic that will be happening just to prepare your program or your binary just to be run on your computer. So we'll be working through all of that, through like all of this later on. But at the end of the process, there is a machine code in a file, like we have seen that. At the end, you will be finding this. So, um, the operating system actually loads this machine code into the RAM and instructs the CPU to jump the instruction pointer to a position in RAM. And then the CPU just continues running its fetch execute cycle as usual. So the program begins executing. So what does that mean? So actually, the operating system is the one that is supposed to take this machine code and put it into the RAM, and then the processor will be trying to execute this. So this is one of the few like questions or moments for me. Like seriously, like this is how the program you are using to read, for example, I don't know, or using to watch this video, you are like running now is your CPU is fetching your browser instruction from RAM in a sequence like directly executing them and they are rendering this article. So just imagine this. Like, imagine this is your RAM, uh, this is your RAM. This is like your okay. Take off that. This is your RAM. Let's say you have, for example, I don't know, C7. It has this instruction into the RAM 8375. I don't know. 65. This is kind of instruction, and the instruction pointer now is at this place. Let's say it's at this place. This is where the instruction pointer is pointing to. It's pointing to the 78, and then it will be pointing to the 89, and then it will be pointing to the 09, etc., etc. So it turns out that CPUs have a super basic world overview. Like, they only see the current instruction pointer and a bit of internal states. Like processors, well, or processes are like entirely like operating systems abstractions, like not something CPUs natively understand or keep track of. And we will be going more into in depth about processes. A process is something is something called when we try to um, just load a program into a RAM. When we load the program into RAM, it becomes called or the naming of that thing is a process, and the one who is responsible to load the program into the RAM is the operating system. Yes. So I think you should just shout out to the operating system for doing a lot of things for you. So for me, this raises more questions than just some bunch of answers. So the first question that we have to ask is if the CPU doesn't know about multiprocessing and just executes instructions sequentially, why doesn't it get stuck inside whatever program it's running, which is a really interesting question. And how can multiple programs run at once? And I don't know if a program is running directly on the CPU and the CPU can directly access RAM, I'm sorry. Why can't code access memory from other processes? Or I don't know who is the one who is forbidding all of that. Is it something called the kernel? And we will be trying to see what the kernel is, or just an overview. Um, speaking like of which, what is the mechanism like that is preventing every process from running any instruction and doing anything to your computer? Um, and what is a damn syscall? That is something that I've been using a lot. What is a syscall? Like the question about memory, like I think deserves its own video, and I think I'll be covering it later in one video alone. And I think just to explain it a little, it's like the majority of memory addresses actually go through a layer of misdirection that remaps the entire address based on what I will be trying to explain that in one video called the memory management. Don't worry. So for now, just forget all what I just all what I just said for you. But for now, we are going just to pretend that programs can access all RAM directly and computers can only run one process at once. And we will explain just with me, I will be trying to explain just these assumptions and time. So it's time, I think, to go through our first our first hole, which is the land filled with syscalls and security rings and kernels and all of that. It's time to do that. Yeah. So aside, the first question is what is a kernel? Now, this is one of the fewest things that I've been listening, or that the word is so famous. Like everyone is saying, like kernel, kernel, kernel. What is a kernel? So your computer's operating system, I don't know, like Mac OS, Windows, or Linux. I know what kind of operating system you have is like a collection of software, like I don't know, that runs on a computer and makes all the basic stuff work. So basic stuff is a really general term, and so is operating system. I don't know, depending on who you ask, it can include such things. I don't know, include such things like apps, the apps that you are using. For example, this one, the fonts. I don't know, this font, for example, of the Chrome. I don't know, the icons, with a lot of stuff. Actually, operating system, for example, Chrome is not embedded into the operating system because it's a program that I have installed aside from the operating system. But okay. operating system comes with a lot of softwares too. So the kernel, however, is the core of the operating system. It's the main software of the operating system. When you boot up your computer, for example, the instruction pointer, do you remember the instruction pointer? This one, the instruction pointer, yeah. The instruction pointer um, is actually like starting at a program somewhere. That program is actually called the kernel. So the kernel is a batch of code that has near full access to your computer memory. I don't know, peripherals like your mouse, keyboard, screen, etc., and other resources. And it's like the one who is in charge of running software installed on your computer, um, known as user mode applications. We'll be trying to dive more into that. So we will learn just how the kernel has this access and how, for example, user lands or user mode application or programs don't. So Linux, for example, is just a kernel and needs plenty of user land softwares like shells, display servers to be usable. So the kernel in Mac OS, for example, is called XNU. For example, you can just Google it, XNU. So XNU is the kernel of the Mac OS, um, and is a Unix-like basically. And the modern Windows, for example, kernel is called the NT kernel. So it's the main software that is responsible for operating the operating system itself. You see, it's the Windows NT kernel. So this is basically what a kernel is. I think just after watching this video, I suppose you should be able to understand what a kernel is. Just one more thing to mention is it's okay if you take notes just when listening to me. You can take notes and understand more what's happening just by researching more on the internet as I did. So, two rings now, just to explain all of this. Security rings, the mode sometimes called privilege level or rank, is a processor and it's controls I think a lot of what's happening. So just to explain more what are security rings, can get that. This is the best picture that you can have. So, as you can see, we have modes. We have a kernel mode, forget about the ring 1, ring 2 for now, and we have a ring 3. And now we have something called privileges. So, this is the least privilege, this is the most privileged, I'm sorry. So as you can see, the kernel is the most privileged and the application is the least privileged. So these are called security rings. So modern architectures have at least two options, which are the kernel or the supervisor mode, which is the same as ring 0, and a user mode, which is the same as ring 3. While an architecture might support more than two modes, only kernel mode and user mode I think that are commonly used these days. So for example, in the kernel mode, anything goes. For example, the CPU is allowed to execute any supported instruction and access any kind of memory. And for example, in the user mode, only a subset of instructions is allowed. For example, input, output, and memory access is limited. It's not like in the kernel mode. So, for example, when you are in the kernel mode, you are like in the beast mode. And when you are in the ring 3, which is the application or the user mode, it's like in the sheep mode. Yeah. So, generally, the kernel and drivers run in kernel mode while applications run in user mode. So, drivers are the kind of softwares that will make, for example, your mouse or your keyboard um, understandable by the CPU or the CPU or your program or your I don't know your computer basically can understand a keyboard or a mouse using something called a driver. So a driver is also a piece of code that has been coded by the manufacturer of the hardware itself, and he is delivering it to the users to install to make their computers understand the mouse or the keyboard or anything related to hardware. Yeah. So processor starts in kernel mode before executing a program. So there is one thing that we need to understand too is that processors have two modes, which are kernel mode or user mode. So processors when we start the computer are are starting in kernel mode. Just before executing a program, the kernel initiates the switch to user mode. So, for example, when I try, I don't know, to open any kind of software, let's just say, I don't know, let's open a new tab. When I open a new tab, it's actually the processor switching to the user mode. So, like, imagine this like conversation between, like, let's suppose we are now in the kernel mode, and like I say, um, in the kernel mode, like I saying, I want to read from a protected memory. Hey kernel, could you please um, give me this value in this memory? And the kernel will answer with a simple, pretty simple answer, like saying, okay, here you go, take this memory. You can just read from it. Since I'm the kernel mode, since I'm in the kernel mode, I'm sorry. And imagine now I'm in the user mode. When I'm in the user mode, like for example, I want to read this protected memory. Like I'm saying to the computer, I want to read from this protected memory. He's going to say me a pretty famous answer, which is segmentation fault. So segmentation fault is like saying you cannot access a specific memory as long as you are in the user mode. But if you were in the kernel mode, like there's nothing called segmentation fault. You can read whatever you have in your RAM. So that's why basically when you try to allow something, well, let's just say you are trying to allocate some data in an array where you are trying, I don't know, to code in C, C++, or whatever kind of language you have. And let's say you allowed or you allocated, like say 10, I don't know, 10 chunks of integers, an array of 10. And then, for example, when you try to access the 11th element, it's saying like segmentation fault. You cannot access that. That's basically because you are in the user mode programs. So basically your program is running in the user mode. That's why it's not going to allow you to read from that memory right to that memory. So an example of how processor modes manifest actually in real architectures. For example, on the 86 we have something called the CPL, which is the um, which is actually the comprehensive. I don't remember. Just let me find that. I don't remember names. CPL, Intel, current privilege level. Yeah. So we have the current privilege level, which is the CPL that can be read from a register called. I remember. Let me remember this. It's the CS, I think. Yes, the CS. Yeah. So the CPL, which is the current privilege level, can be read, for example, from a register called CS in the 86. So the CS is the code segment. So, for example, when you read the 86, uh, when you read from the 86, like the current privilege level, you can just read that value or the current privilege level from that register, which is the CS. It's actually an internally or an internal registers in the AC in the 86, and specifically, the CPL is contained in the two least significant bits of the CS register. So, for example, when you have, for example, this value in the CS when you try to debug or run a program and you check, for example, this is basically the least privilege. This is the current privilege level. So, for example, when you find 3 like that, it's actually running in the ring 3, which is the user mode. For example, if you find 00 like that, it's actually running on the ring 0, which is the kernel mode. So this is basically how the whole program is working. It's a lot of simple stuff he's like doing, but if you go deep down, you find a lot of abstractions. But this is how basically he's differentiating between kernel mode and user mode. Yeah. So these two bits can store like 4 possible rings, like ring 0, ring 1, ring 2, ring 3, and so on. So ring 1 and 2 are designed, like as we said, for just running drivers, but are only used by a handful of older niche operating systems. So if these CPL bits are 1 1, as we have said, like it's going to give you like the ring 3, which is the user mode. If it's going to give you Like if you have double zero like that, then it's going to turn out to be the kernel mode. Yeah. Now, I suppose after just listening to me, you now have an understanding about what a kernel mode is and what a I mean, what a user mode is. Now, another interesting concept is the syscall. What is a syscall? Now, a syscall is something that is in the same horizon of the kernel mode and the user mode. Now let's see, or let's try to find out what a syscall is doing exactly. So programs run in user mode because of a security thing, because we cannot trust every application that is running on your computer or on my computer. So and I cannot give it full access to the computer, so that's why user mode exists. So user mode does its job just preventing access, I don't know, to the most of the computer, but programs needs to be able to access input and output too. For example, my program needs to read from the keyboard and one needs to write to the screen. So this is why and it wants also to allocate memory and interact with the operating system somehow. So to do so, software running in user mode has to ask the operating system kernel for help. Hey, could you help me? I want to read something from the keyboard. Hey, could you help me? I want to write something to the screen. So the operating system can then implement its own security protections to prevent programs from doing anything malicious. So for example, if you have ever written code that interacts with the operating system, let's say you are probably just recognizing one of the majority of these functions that I will be telling you, like for example, read, write, I don't know, printf in C, scanf in C, for example. These kind of functions are actually interacting directly with the operating system. Like there is below a couple of layers of abstractions behind these functions, but all of them actually uses something called system calls. So system calls is a way that can let you communicate with the kernel directly. So for example, let's say you are now, I don't know, just a little example is, let's say you are now having, let's say you are having a user mode application. For example, I don't know, user mode application, for example, that is just printing hello world. This hello world is basically, let me just write that in here. Let's say, for example, you have a function, user mode. This function that is going to be like printing hello world. For example, when you try to print this hello world, actually what the program is going to do while it's executing, it's going to switch to something called, actually let's call it a printf, which is better. When you do printf, for example, it's going to call something a syscall. It's going to do something pretty obvious, which is not that obvious actually, but it's going to do something called a syscall. So it's going to do a syscall to write something to the screen. What does that mean? It's going to tell the operating system to, could you like, this is the question, like this is the question that it's going to tell, could you please, like like write this string for me, like that, like it's going to say that to the operating system. And the so the syscall is basically like saying that to the operating system. Like he's going to ask that question to the operating system, and the operating system will be just answering that. So when we say like, could you please, when you are like talking to the operating system, who is the one that you think is going to serve like the guardian of the operating system. Like actually, could you please, or could you kernel please, or kernel could you please? Actually, you are asking the kernel. So system calls basically are a way of just communicating with the kernel. So it's a kind of special procedure that lets a program start a transition like from user mode or user space to kernel space, like jumping from the program's code into the operating system code. And actually, when you tell the operating system, like, could you please write something, the code that is going to be writing something in the screen is already in the operating system pre-implemented by the one who wrote actually the kernel or the one who implemented the kernel of that operating system. So going from user space to kernel space actually controls transfer to um, actually controlling transfer to the behavior of the program, yes. So, and these control transfer are accomplished just using a processor feature called software interrupts. So, yes, we have something called software interrupts too. See, it's just so fascinating that computer is working. Like a lot of stuff is happening behind your computer that you do not know. Maybe it's time to find them. So, software interrupt. So software interrupts are actually like a way to just say to the operating system or to the processor like to stop from doing the thing that he's doing and start executing what I want to do. So for example, during the boot process, the operating system like stores a table. It's called the interrupt vector table, which is the IVT. You can just find that out, the IVT or the interrupt table for the 86. So the interrupt vector table, the interrupt vector table, which is this one, um, has actually a lot and a lot of values inside of it, and in the this is actually called in the 86, and there is one that is called also in the 64 architecture is called the interrupt descriptor table. For example, we can say the other one too, descriptor descriptor table. Yes. So the interrupt is descriptor table in RAM and registers it, for example, with the CPU. So what does that mean? So the IVT actually is like a way just to map. Instead is a it means just search for a function or a better way. There is any kind of image that is. Let me just check that out. Okay. See the vector table. We find something more meaningful than this. Okay, I think this is a good one. Okay, so what do we have now? So these are called the interrupt source, and this is the interrupt vector. So actually, it's a kind of mapping. So the IVT maps the interrupt numbers to the handler code pointers. The handler code pointers in this place are called the interrupt source. So the userland programs now can use an instructions like, for example, interrupt in assembly, like this, just which tells like the processor to look up to the given interrupt number. For example, when I say like, for example, 80, it's going to check this interrupt vector and goes, let's say, for example, I'm going to give him like 0x2, 0x2. He's going actually to do the timer 1 interrupt source. So this is going to control the processor to look up the given interrupt number in the IVT and switch to the kernel mode and then jump the instruction pointer to the memory address stored in the IVT. So what does this mean actually? So this means when I do a syscall like interrupt 0x2, it's going to execute the code that is pointed by, for example, this one, like multiplier. When I do 0x3, it's going to jump or it's going to switch first the CPU to the kernel mode, and it's going to jump to this block of code that is pointed to by the multiplier. Yes. So this is what basically will be happening. Same goes for any kind of syscalls exists. So the instruction pointer is the one who is going to jump to that specific operating system code. So when the kernel code, for example, finishes, it uses an instructions like return, like this one they will be seeing in assembly, just to tell. Actually, I think it's not the return. Is it I return? I return, yeah. It's I return, yeah. I read. So to tell the CPU, for example, to switch back to user mode and return the instruction pointer to where it was when the interrupt was triggered. So that means that syscalls are way just to jump from the actual program code to the kernel code. So it's a kind of gate, or it's a kind of tool that can help us go from user mode to kernel mode. And when we go to the kernel mode, we actually start executing kernel code. This is really interesting actually. So I don't know if you were curious, but the interrupted ID used for system calls like on Linux is 0x80. For example, when you do 0x80, you actually start doing another syscalls. So this 0x80 syscall is called the ID that is used for system calls on Linux, for example. For example, when you want to do a syscall, for example, on Linux, you should have an interrupt 0x80, but you should also fill the syscall that you want to do. For example, you want to do a syscall for write. Let's say you want to do that. How can you do that? So you got to check the syscall table for Linux. You can check that in this place, which is the Chromium documentation. You can just go, for example, to the 86. Let's say you are, for example, working on the 86, just a 32-bit architecture, and you want to do, for example, a syscall to exit. So to do a syscall for exit, you have to fill the register EIX with 1. You have to pass the error code, which is the argument to the EBX, and that's it. For example, to do that in assembly, okay, we can do this. I can do that for you just to learn how to do a syscall in low level. It's pretty easy. So to do that, all you have to do is just, for example, move into EIX 0x1 and then move into EBX 0x, I don't know, the error code. For example, when you do like exit, this is basically how you do it in high level. For example, 32, you actually need to pass that 32 to um, to the code also, which is the EBX. You see that 32 is passed like the EBX. So this is basically how you try to reverse engineer the stuff. You try to see it in high level and then you try to code it in low level. And once you see the low level, you can go back and find out the high level code. I'm gonna be just using 9. So you can just do a 9. And then once you have just filled the registers needed for that specific syscall, all what you need to do now is just go and do like 0x80. What the processor is going to do, he's going to check the IVT, which is the interrupt vector table, and he's going to check that the 0x80 is going to do one of these syscalls in this place. So this is basically what is happening when you try to do a syscall, and printf and scanf, when they are implemented, are actually doing this syscall too. So basically it's a kind of abstraction layer that gives developer um, the way they want to develop stuff without thinking of what's happening underhood. So it's a kind of API. Yeah, that's why we now it's time to talk about APIs. So just a little explanation about what an API is, just for someone who is completely beginner and does not know what an API is. Just think of an API as of a little box that will be doing stuff. So for example, let's suppose you are now using your phone and you have like a weather application that gives you the weather or the current weather that you have right now on your phone. So to do that, you basically need to um, just use the application, and what the application is going to do, it's going to use, for example, Google API. For example, this is going to use Google API. So what is Google API is doing is it will be getting the current location and do a lot of its magic and gives you the weather at that location. Just imagine it as a black box. You don't have to understand a lot of what's happening inside the API, but think of what's going to be the input and what's going to be the output, and just play around that. Yeah. So the same goes when trying to deal with computers. So there is an APIs, and it's a kind of abstracting um, it's a kind of abstraction that is going to abstract a lot of interrupts in front of you. You don't have to always like do move EIX, EBX to do any kind of thing. It's time to just use exit. So exit is a kind of API now. You give it the 9, you call the exit, and it's going to do all of that for you. So here's what we know so far like about system calls. Like now, system calls like user mode programs cannot access input output like for memory directly, so they have to ask the operating system like for help to interact with the outside world. Programs can delegate control to the operating system like with special machine code instructions, like for example the interrupt, the I return to return back to the user mode. We also learned that programs cannot directly switch privilege levels, like software interrupts are safe because the processor has been pre-configured by the operating system. So where in the operating system code to jump to, so the interrupt vector table can also help us and can only be configured from the kernel mode. So for example, if you want to switch an entry or you want to modify an entry in the um, in the in the vector table or in the interrupt vector table, the one that can do that is actually the operating system. You cannot do that. So programs need to pass data to the operating system when trying to trigger anything like a syscall or anything, as we can see in this example. So the operating system needs to know which specific system call to execute. You can check that from the table. And for example, I have just showed you how to, for example, do a syscall to exit, for example. Um, so the mechanism for passing this data actually varies, I think, by the operating system and the architecture itself, but it's usually done just by placing some data, as we can see, like in registers. Just placing them like in certain registers, or maybe sometimes you can just pass them to something called stack. We'll be trying to see also in the next videos. So yes, this is actually what is mostly happening. So yeah. So many, I think now, processors such as the Intel um, called CISC architectures, which are complex architecture. I remember, I don't remember actually the S and the C what are referred to, but I think we can just Google them. CISC. 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 Yeah, complex instruction set computer. Yeah. So many like complex instruction set computer architectures like the 8664 that I have been talking about a lot contain instructions designed just for system calls and created due to the prevalence, I don't know, of the system call or something like that. So for example, Intel and AMD are like managed not to just coordinate very well with the 8664, and it actually has two sets of optimized system call instructions. For example, syscall and sysenter are like optimized alternative of this interrupt 0x80, and I think instructions like int 0x80 are much more slow compared to the syscall and the sysenter. So the corresponding return instructions, like for example, we have the iret, we have the also the, for example, the alternative for this one can be, we can find for example sysenter. We can also find I don't know, syscall. So you can find, for example, syscall and sysenter. For example, that's in the 8664. You can find sysenter and syscall. We can also find, for example, for the iret, you can find sysret. You can also find, I don't know, sysexit, for example, too. Um, Actually, these instructions are designed to just transition quickly back to the user space and resume program code. So AMD and Intel processors have slightly different compatibility with these instructions. Syscall, for example, is generally best option for 64-bit programs, while sysenter has better support um, with 32-bit programs. So, for example, the representative style, for example, or the other world of architecture is called the RISC. So the RISC is the reduced instruction set for computers. So, for example, we can find ARM processors that are using the RISC architecture tend not to have such instructions, and the RISC architectures is used, I think they are used a lot in the Apple Silicon Valley, I think. Yeah, they are used a lot in the Apple Silicon, and it's based on that actually. So it uses only one interrupt, I think, of instructions. I don't remember a lot of the RISC actually, but yes, I know ARM, but I'm not like used to use a lot of Mac and a lot of Mac architectures and a lot of Apple architectures. I'm sorry. So for syscalls and software interrupts, they think they are much more alike. Yeah, but I think my Mac users are doing fine. Yeah. So just a little conclusion about this video, because before we end it, like here, just because we learned a lot next this video, let's do a brief recap. So processors, I think, execute instructions like in an infinite fetch execute loop, and don't have any concept of operating systems or programs. So processors are dumb for me until now. So the processor's mode usually stored in a register, and it determines what instructions may be executed. Operating system code runs in the kernel mode and switches to user mode when running programs. So to run a binary or a program, the operating switches to user mode and points the processor to the code entry point. I'm sorry, in the RAM. And because I think they only have the privileges of user mode, programs that want to interact, for example, with the keyboard or the mouse or anything, needs to jump to the operating system code for help. So system calls are a standardized way for programs to switch from user mode to kernel mode and into operating system code. So programs, I think, typically now just uses a lot of syscalls by calling something called shared libraries functions, for example, the stdlib, the stdu, etc. This wrap machines code for either software interrupts or architecture-specific syscall instructions that transfer control to the operating system kernel and switch ranks. So the kernel does its business actually and switches back, I don't know, to user mode or returns to the program code. So it's time to give a little shout out to the kernel for doing a lot of things for us until now. And yes. So so the answer to this, I don't know, to a lot of questions and that has been in my head. I think I've tried to answer them in one video. I don't know if you learned something new or not, but this is basically what I wanted to share in this video, and I will be sharing other stuff in the next videos too about we will be trying to dive a little into the execution of the program and the processes and a little bit into what does the kernel can do. And yes, so I think we hit the end of this video, so don't forget to subscribe. Don't forget to, again, don't forget, it's really important to ask questions. If you have any kind of question in your head, put it in the below comments section. And bye.